Hello everyone, I'm SRIVASTAVA, a PhD scholar in EC Department, IIIT Delhi, with my co-author Mohammad Adil ARIF. We both are working under ANUJ sir. Our poster title is Design of Razor Flip-Flop for Speculative Computing. In the last few years, the computational capability of mobile phones and handheld devices have phenomenally improved at the rate given by Moore's law. However, with the 65 nanometer node or higher transistor level integration, power consumption of processors have actually worsened at aggressive process nodes. That is, more transistors can now be fitted on a die. However, they cannot be used due to strict power limits. In this poster, we will discuss about adaptive design techniques, which provides up to 50% of power savings. Power consumption issues are further increased by variation in transistor performance at aggressive geometries. The sources of radiation can be global or local in extent, or static or dynamic in nature. While the practice of adding a safety margin or guard band to supply voltage leads to robust circuit operation in presence of radiations, but it also leads to higher power consumption. Circuits exhibit worst-case delays for very specific instructions, and hence, for most of the computations, they contribute only to power wastage. This growing energy waste has led us to adaptive design approach, which tunes system parameter, that is supply voltage and frequency of operation, during the dynamic operation of the processor. First, always correct or canary circuits. It has a replica of a speed limiting critical paths and is monitored for timing failures as the supply voltage is scaled. Scaling is limited where the replica path just begins to experience timing failures. Let fail and correct. Razor. It reduces voltage margins with in-situ error detection and correction for delay failures. It enables operation at a voltage at the edge of failure, that is point of first failure. The operation principle of razor flip-flop is shown, and the relationship between the supply voltage, energy consumption, and the pipeline throughput of razor-enabled processor is shown. The margin is much higher than voltage of first failure under typical conditions because of safety margins. The total energy of the processor, that is E total, is the sum of energy required to perform standard processor operations, that is EPROC, and the energy consumed in recovery from timing errors, that is E-recovery. As the supply voltage is scaled, the processor energy EPROC reduces with voltage. However, as the voltage is scaled below the point of first failure, a number of significant paths will start to fail to meet, a number of paths fail to meet timing. Hence, the error rate at the recovery energy, that is E-recovery, increases exponentially. The total processor energy, that is E total, shown is an optimal point where the rate of change of energy recovery and E-processor offset each other. In the schematic designed in Cadence Virtuoso 65 nanometer technology, two flip-flops are odd together, one running at a slightly delayed clock. Error is generated when there is a mismatch. After then, the signal goes to mux and restores the correct output in the next clock cycle. The total setup for normal flip-flop in this design is mux delay plus setup time of flip-flop. The total setup time for delayed flip-flop is mux delay plus setup time of flip-flop minus clock delay, which gives the extra margin we require for worst case during voltage scaling. The output graph is shown in three cases. First, when timing constraint of both flip-flops are fulfilled, therefore no error is generated. In second case, when timing constraints of only delayed flip-flop is fulfilled, since there is extra margin, error is generated, but output gets corrected in the next cycle as shown in graph. In third, since the timing constraints of both flip-flops have failed, output is changed. So only for a 267.9 picosecond time margin, we can get corrected output. The clock to Q delay is also improved by 47%. For a very specific application part of Razor technique, implementation in SRAM, where voltage scaling was done, and voltage is scaled down as low as 0.6 volts. In this single sense amplifier is used, which needs to be activated twice in the same cycle. For the latching scheme, first SA enabled signal is denoted by SAE0, corresponding to the typical margin, and its delayed version is SAED, corresponding to the burst margin case. The output of the respective latches, LQT1 and LQT2, are then compared to detect the presence of an error. The comparator outputs is sampled at SAED using another latch. Resetting of the error signal is done at the falling edge of the local clock. The error signal generated from all the inputs, IOs and ORs, are odd together to trigger a common error flag. This ensures that even if there is a single error in a single bit, the entire word will be discarded. Only the corrected data, second sample, stays latched at the output so that it is available for the subsequent system access. The error case is similar to a cache miss in a hierarchical memory system wherein the memory is accessed more than once to get the data. Limitations to this Razor flip-flop and references can be discussed further. With this, we end our presentation. Thank you.